Good morning. Unlock 250 bonus bits every 10 subs. What's that? How we doing? Let me update the title. Hopefully that updated. Part 2. Hope everyone's doing well. I figured out the ring situation. So we're mainly going to be working on DNA probably today. Let me turn this down a little bit. Do you guys want music in the background? Let me know in the comments. Because I could find something like that. Um, all right, so let me show you what I figured out with the ring. So, um, turns out I was doing the ring properly. Like I got it to work, but the only thing that I wasn't getting was the stereochemistry. So as you can see, let's see if I can do this real fast. So if we point the hydrogen backwards, right, and we assign rank to these atoms here, so I should really know how to do this. Let's go to the periodic table real fast. So sulfur's right here, so it has a higher priority than a carbon atom. Um, so to go 1, C, so 2, 3. So this would be R, stereochemistry. Let me make sure that's right. Um, um, where would I find that? Um, does it give us the stereochemistry here? There's one paper that lists it all. Um, Let me see if I can find it real fast. Not that one. I just looked at that one. Always check your work. Um, Come on. Um, Maybe it's here. Nope. This is a thesis. Something like this, I remember. Uh, Dang it. go to images. Where would it be? Or maybe it would be, what's his name? Van der Donk. Not that one. I think it's the same paper. Oh, would it be this? Yeah. Okay. So beat this one. So BS. No, this is ring A. So BR. Okay. Right. Okay. Regardless, I know this is the right stereochemistry here. Okay. So the way to enforce this in TLEAP is to use this command I discovered, flip, right there. So when you just like normally bond the two, and I got it from this little back and forth. When you just normally bond the two with TLEAP, it assigns it as S. So selecting this and then flipping it, make it R. So by the end, you get the proper peptide. See if I can find out. Are we signed in? Yeah. Test.pdb. Hide the waters. So this is what it looks like after the first run, right? So you see so we can do it again. 1, 2, 3, R. So I think we figured out the ring. And the simulation runs and it works fine. So that's cool. We can make arbitrarily large rings now. We don't have to parameterize this entire thing, which is what I was used to doing. So progress is being made there. Now what we need to do is figure out what's wrong with the DNA. So I'll go over what we're trying to do briefly. So essentially we have this here, this two-stranded helix. So one has a bunch of A's, the other one has a bunch of D's, right? And we are trying to create this linker here between the two termini. Now, what TLEAP will do when you just feed it the sequence, it'll automatically assign these, or the termini to be DT3 and DA5 or something like that. So to enforce it not to do that, you have to do this here, which I don't quite understand what this function does, but regardless, whenever you do this, the output PDB looks as it should. So we have this phosphate here, so this will bond to the phosphate as you see, and then this CH2 will bind to this ribose right here. Let's look at this atom. Can I see the specific atom? O3 prime. So if we look at TLEAP, we have the combine command. So because we're adding a custom ligand across sequences, you have to use this combine command. And so we're going to bond the C12 of PEG, the linker, to O3 prime. Then we're going to bind the O3 to the phosphate. And for some reason, it enforces a bond between the bottom half. So I don't really understand what's going on there. But regardless, we have our stuff. But whenever you run a simulation with this, like you add waters and stuff, I end up getting this super weird error, which is not present right now, but so let's, while we're talking, go ahead and request access to a GPU. Interactive job. So we want something like that. Yeah. All right. So we can go here and just mimic all of this. So instead of mem per CPU, we could do this. Oops. I guess I'll just have to type it out. CPUs per task equals 24 to nodes equals 1 time, we already have time there, mem 32000, and then gress equals GPU one. Is there anything else? I think that's it. All right, so that'll take however long it does. So I think the way to diagnose this would be to just do it without the linker and see if that runs fine. So we can, we'll open this, and then we'll go to pymul, and then we want to load this. Uh-oh. All right, close that. Okay. So we'll just delete this. Or remove atoms. So we should have just this. So file, export molecule, save, PDB, and we'll do DNA without PEG. We'll save that. Okay, so here we can just so I think we still need to have this in place. This is fine. That's fine, but we need to change this to without. Comment that out. comment that out. This, and then the rest can stay. Okay. Now what does that mean? DNA. Oh. Okay. So let's look at the file it created. We have our mul2. So you see here, it enforced the bond between those two. So one thing that could be an issue, for now we're just going to unbond these two, but one thing that could be an issue, here, let's say if this is a PDB so you can kind of see what I'm talking about. So if you save PDB and then sys, and then we can just do PDB. I think that works. Yeah. Okay. So you can see that it forces a bond between these guys, which it should raise an error. Yeah, there's a bond of 18 angstroms between this. So in tleap, I'm doing delete bond, and this should fix that. Yeah, it does. So we don't see that error anymore. Right. Okay. So I think what we're going to do is just load this in the supercomputer and see if this just runs. Or if we get the same sort of error. Because if it does, then that means there's something wrong with this. And if it doesn't run, then there's something wrong with this and not the PEG. I mean, there could be something wrong with the PEG, but you know what I'm saying. All right, so we'll go to most recently modified. And we will drag these guys. This in there. Nice. Okay, so we have GPU time for an hour. That's clutch. So now we'll do this. We'll do module load. Okay, and we should be able to just run this. They're signaling. So is that the same error that we got last time? Not 100% sure. So let's get rid of the CUDA. See what that does. Okay, so now we're doing minimization and it's going. So the real test is if we can get past this to heating. So let's go ahead and add those heating files. So maybe it is something wrong with the PEG linker then. So I believe it's heat watt after that. but the restraint mask doesn't seem to be a problem. We're still, yeah, we're going through minimization just fine, it seems like. All right, so is this the right one? Yeah, min watt RC7. Okay, so we got to change these names here. So let's let this ride out until we get the restart file. Should be any minute. So I don't understand why CUDA threw an error right there, but so yeah, it's probably something with the PEG linker, just from what I can tell right now. Unless there was something wrong with the computer yesterday. Okay. So let's look at, well, let's just see what happens. So we have our restart file. So heat watt.in, so we can remove this CUDA. So this parm needs to change to this. And then everything else should be fine. So let's see what happens. Already we're ahead of what typically what would happen. How many steps do we do of this? A lot. Okay, this seems it's gonna take an hour. We're not gonna wait that long though. Hopefully there'll be just a restart file that comes out. Or does it come out just at the end? Let's wait till we get another step in. I think it's working though, without the PEG. There we go. Okay, that's enough for me to close that. All right, so now let's add back the PEG. So we want that, want that. Let's run tleap again. So there's no crazy bonds. Oh, something we gotta fix. So we want to do width. Okay. So yeah, it does say that there's close context, but that's not really a huge deal, or that might actually be what's causing the issues potentially. Normally it's not a big deal, but maybe in this case it is. So let's drag this back over, replace, replace, replace. All right, so now if this doesn't work, then it's definitely the PEG. We're gonna have to rethink our strategy. And I think another thing that could be wrong is that I have to specify the atom types whenever I'm binding these things together. Right, so I've been getting this right here. Okay. So the only difference is when I added the PEG. So I think the first thing we're going to do is try to specify the types. After bonding. Um, so how do I do that? Or we could do something. Hey, Parakeet. How's it going? You're up early. Um, so maybe I'll just, for the first thing, I'll just move this back a little bit. I have to go to school soon. You sleep okay? With PG. Alright, so nice computer background. You like the Saturn? I was thinking about changing it. It's been my background for a while. I like space stuff. Yeah, me too. Saturn's one of the craziest planets. All right, so we need to show sticks here. Doesn't it have the most moons? I don't know. I don't know that kind of trivia. Maybe. Jupiter might have the most moons. All right. So how do we do this? So I think we want to unbond that. And then we also want to unbond this. Yeah. And then we can scoot this boy back a little bit by just going like how do I do this? There we go. Yeah, just scoot it like that. So there shouldn't be any more close contacts now. Oof, I think I messed up that bond actually. Okay. So let's select this again. Why isn't it working? That's too far. Now we're moving the actual bond itself though. Maybe I select it like that. Come on. Oh, I need to create object probably. And then remove atoms. Pretty sure it was like 60. Never mind. Saturn beats Jupiter with 82. I looked it up. What is this diagram of? This is DNA, and we're trying to simulate it with a linker. Right now, I'm trying to move the atoms away so they don't uh, like bump into each other too much. Because right now, Amber is complaining about stuff. We need to fix that. All right, I think that's probably fine. Let's see if that was the issue. PDB. So we'll save this with PG. Yes, replace. So we'll look at this now. Looks fine to me. Now, could this be an issue? Let's look at the, let's save it as a mol2 real fast. Amber is, no, it's not like a specific kind of DNA. It's just a row of D and T. This is basically like a test system, like, you know, like a very simple one. But Amber is a simulation package for molecular dynamics. You can think of it as like a just like a software package, like what FL Studio would be, but for science. All right, so let's save this as a mol2. So maybe that's the issue. Do we see a crazy bond? No. Chemistry FL Studio. Yeah, basically. It's a good analogy. Um, all right, and does it complain about other stuff? I don't think so. Yeah, it doesn't complain about anything. Okay, so all right, so let's drag this over. Try it again. I have like deja vu right now. Same deal. Yeah. Significant figures and isotopes. Sig figs are, they say sig figs are important, but it depends kind of what you're doing, honestly. Yeah, just pick the one that's the least. You can't go wrong. You're only as accurate as your most accurate decimal. Um, okay, so I don't think the distance to this is a problem. I think now it's the atom types, probably. Um, yeah, I mean, I haven't, you know, um, let's just say it goes down. It gets deep, you know. Sig figs is very early on, but they teach you important stuff. Though it all carries over. Um, all right, so what I'm gonna do now is give this info to Claude, but enjoy the amateur stuff while it lasts. How um, explain the importance. Explain the importance of renaming the atom types here when we form new bonds. All right, so then I want to give it this hybridization state. Yeah. I am attempting to add a linker to DNA. I believe I need to change the atom names here when I add the linker. I am bonding the C2 to the O3 prime of the ribose and the, what is it, O3 to the free phosphate of, I don't know, what would that be? DA. What should I rename the atom types to be? When I run the system without a linker, it goes fine. But when I add the linker, I get this error. I'm taking biology next semester, which I'm interested about. When I was younger, I was like hyperfixing how the human body and stuff, so like I actually enjoy it. Yeah, my brother is a nurse, and he wasn't really interested in science, but he reaches out to me a lot and asks me like cool questions, and we just have conversations about like how interesting all this stuff is. So I feel like that's a lot of people's like gateway into this. Do nurses get paid a lot? It depends. I mean, if you're a travel nurse, yeah, you get paid a lot. But I mean, it's good pay. Like you can live off it for sure. You correct atom types. You're correcting CO ether OP. Here's what you need to add. set sp3. Is it a hydroxyl? I don't even think they protonate it. No. All right, do these carry over though? Like, what does amber call these? C7, oh yeah, I guess so. P, this is OS. Yeah. Okay, rewrite the tleap file in full with these new atom types defined. Hopefully this will work. That kind of makes sense then. Set CT, yeah. 17 OS. Okay. H1. I don't think we need to do some of these on residue 8. Okay, let's just see what happens. All right, have a good one. Well, it ran without errors, so that's good. But now we're getting strange things. P and O3, there's a bond of 23 angstroms. DT9. All right, let's give it this output here. Here, I think I'm gonna do this. So let's change this back, but let's just set the atom types. Because I think that's actually right. So 1703. Yeah. 1603. Let me make sure that's where. So 16 and 1. DT16, DA1. Okay. Why is 17 getting a name? Oh, okay. And this should be 1, I think, not 9. Why would it be 9? Just about that. So we don't need that. We could just rename this 1. Type P. All right, let's see how this goes. No weird errors. What are we saving out? Mul2. So I wonder if we just removed those set names, does it even change the mul2? So let's look here. I didn't see any change. So it seems like they already have the right atom type. Unless it's changing something else, but let's still try it. Where are we at? No. Hmm. How much time do we have? 30 minutes. Hopefully we'll figure it out quickly. So it's not the atom types. I've already done this. I just don't know. I could do like, there's no way that changes anything. Damn, dude. I don't know, man. I mean, it could be like the thing we added here. I doubt that's it too, though. So this one's a dupe of this one that we had to add. Doesn't seem like the issue though. And this has gone through minimization before. I mean, let's just remove that. That's not going to fix it, but. Figured. What if I just loaded the linker? Delete everything. And I just simulate that. Do we already have PEG, PDB? We have that. But that's with the caps and stuff. So what we do is we cleave this right here, or this actually. Cleave that, and then we cleave this right here. Does changing it to GAF1 do anything? No. We're gonna have that there. Doesn't make any sense. PEG a lot. So you can pretty much comment all of that out. And do PEG. Okay, so we just have that. So what does this do? No way this runs. Okay, so that's pretty interesting. Yeah, this goes. Okay, so it's got to be how we're binding the atoms together. This looks fine. So it's not something wrong with the ligand or the linker inherently. There's not something wrong with the structure. So it must be something wrong with how we're combining them together with the bond commands and stuff. Okay. We're doing some detective work right now. Okay, so there's got to be something wrong with this works, this delete bond command. We might need this. Let's get rid of all those comments. All right, let's build the structure again. All right, so we have DNA alpha fold. Okay, so this is what we're starting with. All right, and then we can go to PEG and then add the new cartoon, I believe. Yeah. Okay. And so we can either do it to here and there, here and there, or here and there. So we'll do it to the bottom. Okay, so we have these here. Send this in. Hide cartoon. All right, so here's our stuff. So we need to flip this around. Like that. And then we essentially need to bring this up. So move that. It's too close. Like that. So this is far away, but I think it's close enough to do its thing. Okay, so we'll do file, export structure, export molecule, save, PDB. I'm gonna go back one. So DNA with PEG, save. Yes. All right, so we can look here. So we want to bind C12. So DNA with PEG. So let's do this first. It could be something like this going on. Like, why do we need that? I'm not sure why we need that. We'll just change this to DNA. Okay, we could just get rid of these for now. All right, so let's do this. All right, so then we'll do DESC1 or DNA. Okay, so PEG will be 17 then. So bond PEG. So this should be 17. This actually should be DNA. DNA 17 C12 DNA. And so this will be, what are we doing? C12. And this will go to O3 prime of 8. Or what is this? This is DT. So it should be 9 actually. Yeah. But it's 8 of this. So maybe it's 16? Yeah, I think it's 16 actually. Pretty sure. And then this will be DNA 17. And this one here is called O3. And this will go to 1. And then we'll just comment this out for now, but let's see if this command works. It does. Okay. So we'll quit that. Tleap minus F. Tleap. 0 errors. Okay. There's a bond. That makes sense. That's fine. And we didn't need this. All right, so let's open this up. Let's give it the files again. Where are they? Hello? Why can't I drag this over? Why aren't you working? Do you reload window? You were just working a second ago. What? Why? Why can't I drag and drop anymore? Oh my God. Does anyone know what's going on? I mean, I could do this to the terminal, but I don't know how to do that. I have 9 minutes left. Of course it doesn't now. It's not working at all. There's something wrong with VS Code. There we go. Now it works. It's just weird shit like that. Drives me up a wall. How much time left? That's over. Oh. Please be nice to me. Oh, we're back. It's never like that. Highs and lows. All right. No. We want Alex. Damn it. What happened? What'd I do? What'd I do? I have no idea. I have absolutely no idea what's going on with that. Please work, please work, please work. What? Oh, no way. Don't you dare edge me right now. Oh my God. Is it real? Holy shit. Let me just make sure this is real. It looks real to me. Oh, let's go. Yes. Finally. All right, we learned a lot though. So I was doing it right. I mean, I wasn't clearly, but um, the thing I was missing, it was probably something stupid. Like I was assigning the wrong thing, like assigning the wrong residue or something like that. But everything else before then seems fine. So here's what we can do now. Make arbitrarily large rings and uh, assign stereochemistry. And then the other thing we can do is create custom linkers between chains. So huge unlocks. Um, I mean, at this point, I feel like I can simulate just about anything. Or at least get it to run, you know. Um, but that's like half the battle, frankly. Okay, let's look at the output here. Let's not get too happy. Nice. Look at that. Hell yeah, dude. That's so cool. Man, that's sweet. We can simulate DNA linkers. Let's just be 100% certain. Let's go to here. Feels good. Feels good. All right, so what do we do next? Um, so now I think we need to set up some more simulations with Hallam 2. Um, I need to use the bathroom. We could set up a simulation with just the peptide, because my collaborator wants to see that. And then we need to start making a study guide for my oral examination. Pause. So what do we do first? I think we set up the Hallam 2 simulation. I don't think it'll take very long. Um, Another thing we need to do is cross-reference our charges for um, for dihydrobutyrene and see if it matches the expected charges in the paper. So that's another thing we probably have to do. And then we need to do uh, dehydrated serine. So, um, yeah, this is working. So I'll just cut it out, cut it off here. Sweet. So I gotta send this off to people. I'll hold off on this. But all right, let's get to work. So get out of that. Um, this can stay there. Do we need to create a new directory? I don't think so. It's still kind of what I'm trying to investigate. Sync handoff. Okay. So yeah, we could do it right here. Yeah. Conda, activate Amber. Um, so I almost feel like we can dupe um, maybe the unmodified version and just rename the stuff. Like that's a good starting geometry. Um, yeah, yeah, let's just do that. Or we could just run them all back. Nah. Yeah, I think we'll just do that. Yeah, okay. All right. All right, all right, all right. Sync. Um, dir unmodified. Let's do zn bound. Call it that. So we'll open this. So everything in here, except results, it's fine. We'll override it. Paste it in here. We can go into here and just delete that. Just delete all those. It's fine. Okay. So now we are going to go to this input file, which is called the output, funny enough. And so we want to rename histidine, which one? So we want to name 849. Why is Siri going on? Histidine 849 or 894. Yeah, 894. 4. So this should be HIE. And then this CYS 848 or 8. Yeah, 848. Should be CYM. So what this will do is enforce the coordination of these residues to the sink. So we got CYS 893. Change that to CYM. Okay, these are CYM. And then that should be it, honestly. I could change this back to CYS. That might be a move. Should I do that? Why would I want to do that? I think we just leave them, just so it's more comparable to the other simulation. That's my argument. So now we can do T-leap again. Room results. It's minus F. All right. First things first. We need to do that. See what the charge is. 26. So it changed because I added more CYM residues. No solvent present, add solvent first. Oh. What's that? Failed to generate. Oh, okay. All right. So we don't have an HG there. Just delete those. All right, so here is the volume. So we can do this math here. That. So it'd be 218 plus 26. 244. I'll comment that. Okay. Then we can do this. All right, so now double check the output file here. So all looks good. Got a magnesium there. What we got here? HIE. Yep. We got CYM, CYM. What is this? HIP. So it's titratable. That should be titratable as well. So 647. Oh, it's not. Yeah, that's probably fine. All right. So I think we're ready to send her. CPIM was fine. So now what we do, just drop this off. Into here. So now I can drag and drop for some reason. Okay. I'm gonna go to the restroom. So in the meantime, you can just stare at this. Sorry. So that's done. So we can go here. So we can automate the submissions. Tmux. There we go. Okay. So should I add another one? I don't know. Probably not. I don't really see the point. What I'm really curious to see about this though is, for one, do we dehydrate here? Does this get close to that? And um, what happens over here? Like, are there secondary structures that form? And if there are, does it give rise to potentially another ATP binding site? All right. So what's the next thing that we can do? It's already running. Nice. Um, so we can do the fully modified peptide now, I think. So yeah, let's go for that. Mm, do we make a directory here? Yeah, I guess so. So we'll do, I guess we'll call it HAL A2. And I'm going to start putting the date on things. So it'd be 10, 30, 25. All right. So what do we need to drag in here? Rings, probably this. Or no. This. Yeah. Um, do we do this whole thing? I guess so. We could probably clean it up a little bit though, which I'll do in a second. Okay. So let's see what we got going on here. So what does GDP look like? This all looks fine. First off, let's check and see what these charges are compared to the ones that they calculated here. Maybe it's this. No. That? Yeah. So I think we should probably read this. Um, okay. Bacterial, yeah. So it's all just background. In this work, we computationally characterize DHA, DHB to report a new set of charm parameters. As the of niacin. Okay. The established procedure for introducing new chemical groups. The target group with acetylated, these N groups were chosen over methyl groups so that the effect of any double bonds would be accounted for. Yep. Containing the starting guess for topology charges and parameters. ParamChem. A ParamChem project aims to automate with analogies. Due to the unusual double bond, there was no suitable analogies. Penalties under 10 are considered reasonable. Confirming the need for further, or consider reasonable, confirming the need for further parameterization. Dihedral. The force constants Kb, K, theta. We'll optimize. Okay. The initial partial charges were chosen by analogy. With pre-existing chemical groups and optimized to reproduce the interaction distances and energies calculated level between hydrogen bond donors and acceptors and single water molecules in tip 3G. Okay. Nice. So they just put waters there. Further details of partial charge are available in the literature for 3. The confirmation to resolve this issue. By hand. Form using QChem. What is QChem? Never heard of that. Wonder why they didn't use Gaussian. Okay. Um, they're like slightly different. Yeah, the differences right there. Okay. Um, so let's take a look at their SI right here. C2. So that's their whatchamacallit, their capping atom. So I wonder if we, okay. So we have different charges for those. So what would this be? This would be the ace cap. -270. Do we have anything like that? So that would be C5. -2, -366. So that's charm, right? For amber, do I have this up? Yeah, I actually do. No? I gotta have it up somewhere. I guess not. Amber custom residue tutorial. Right, so there are the charges here. Yeah, so -0.3662. So mine exactly matches what amber's is supposed to be. Whereas theirs, oh, this is the initial guess. Oh. So based on DHA. So what's the real one then? Okay. Mm. So I guess it's this one. Maybe this one. So let's look at the nitrogen atom. -0.670. So my equivalent would be this one, N1. Yeah, so we're getting different charges there. What about Ca? 310. C3 negative. Interesting. We could do one more thing. But these are charm. Like, I think they're gonna be different. Maybe we can ask ChatGPT. Are charm partial going, partial charges going to be different than amber? Yes. Amber. Skill to interaction energies. Environmental context. And yeah, I guess that makes sense. Solution environment. Okay, so they consider solvent then. Hmm. Okay. All right, so let's run this back then. So what do we have here? We usually have a ZNB PDB. Ugh. So looks like that. This is from Automated Topology Builder. So I think we can do a structure search here and find it. Um, Net charge 0. So we'll just paste this. There we go. Show molecule page. And also add to saved molecules. I'll do that. Okay. I'm not logged in. Format GramMax. Lamps. So I guess let me log in. So is it going to be in my saved molecules? Nope. I think it'd be that one though. So here we're just being thorough. We want to see just basically the options for this. Add to saved molecules. There we go. All right. Usually they show like a bunch of other ones. What's the molecular formula? There we go. Yeah, so that's our stuff right there. So what I'm going to do actually is open this up in a new tab. Then, so the only difference between this and dehydroalanine is just removing this methyl right here. So we're going to do that. I think if you go here, oh, it's not going to work. I mean, can't I just, yeah, just remove? It'd be -1 carbon and -2 hydrogens, right? Because there'd be a hydrogen here. So 1, 2, 3, let's just say 3, then a carbon, and add a hydrogen. Yeah, so it'd be C6H 10. So let's just do that then. C6H10. Okay, so a bunch of people have done this. A ton of people. I mean, it's probably like one of the first custom residues you would add. So instead of ZDB, we can do DHA. Touch DHA dot or ATB. Yeah, dot PDB. Okay. Oof. Okay, that's not the right thing. We have a isomer. Yes. I have an isomer. Yeah, so we don't want to do that one. Hopefully they're not all like that, and I just picked the wrong one. The formula could be wrong, actually. I don't think so, though. One, two, three, four, five. 1, 2, 3, 6. And then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. All right, come on, bro. That's another isomer. I think we're just gonna have to submit and draw this out. All right, so boom, in there, bond. O, H, H, H. Well, I guess I don't really need that. Put that as an O. Right? Yeah. So let me copy that. Then put this. Where's DHA? Let's see what this looks like. Yeah, looks right to me. Great. Okay, so we have this. Add to saved molecules. Show molecule page. Two acetamido N methyl acrylamide. Okay. Um, yeah, that's pretty good, right? Very low. Um, what I want to do is, so I'll copy this PDB. I want to see the other options though. Um, so I think we can go to structure search, paste that in. Oops, I was supposed to put the net charge there. I think this will bring me actually to the same place. Maybe I could search it like that. Okay, can exit out of that. See if this works. Um, maybe I need to delete this. Nothing. Okay. Oh, maybe it needs to be that. There we go. Um, are there a lot of things with the same key? And then maybe we add the formula to it as well. Dang it. How do we see like other submissions? Mole ID? Just has one. Hmm. I want to see like other. I know other people have done this. Hmm. I mean, do I just keep clicking through? I guess. I think that's what I have to do. God, I wish this website didn't take forever. I mean, honestly, this is probably good enough, but I just want to be extra sure. So we've already done like the first these. So let's do this one. Come on, bro. If it takes this long, it's just not even worth it, honestly. Yeah, it's taking way too long. And there's so many isomers, I think we're gonna have to just go with it. It's pretty low energy, so it's fine, probably. All right, so how do we do this? First off, we need to say this is a mol2. So let's open this. Drag this over. Pymol. And then we will drag this over here. File. Save. Mol2. And then we will name it DHA underscore ATB dot, well, we don't have to do that. Save. We should have our mol2 there. Looks nice. Okay. Let me go here. So we're going to do DHA ATB mol2. We need to find the cap atoms. Which we can get from here. So that's for ZDB. So we touch. And do DHA. Okay, so we need to look here and have this on the right side, left side. That, okay, so this is the ACE part. So this atom is C, well, I guess we start with O, O2, C5, C6, we get H10, 8, 8, 9, 10. So for NME, be N1, H4, C1. We get 2, 1, 2, and then 3. Yeah. Okay. So then we can go here, plug that in. The name of it will be DHA. This will be DHA. Then all these settings can be fine. We have two-stage RESP. So we'll do conda deactivate, conda env list, conda activate that Python sci4. All right, hopefully this won't take long. Should I? Okay, it's done. So now we can look at the charges here and see how they match up to the ones found here. Please don't take forever. So we can look at the ITP file. Here are the charges. So we're looking for that H7C3 0. So they're pretty different, honestly. Negative. That one's pretty similar. But a lot of it comes down to what we're forcing these ACE groups to be. So they're going to have different charges, but I don't know. I guess it's fine. I mean, they look pretty reasonable to me. How do they compare to these, actually? I wonder why these are so different. I should probably do DHA again. Oh, they're just backwards. They're upside down. Huh. They're consistent though. Oh. I think it's fine. Okay. So from here, we need to do some anti-chamber stuff, which looks like this. So we can rename that to DHA. We need to create a main chain file. Touch dha.mc. This is what this one looks like. We can pretty much copy this over to there. And so we can look here. So the head is this guy into the tail C2, main chain C3, and we omit C5. But we're starting from here. We're starting from. We're starting from here. C6. We got H. 8, 9, 10. And then we go to C5. O2. Got nitrogen, so that's N1. H4. Carbon 1. Then we have 1, 2, 1, 2, 3. H1, 2, 3. And the pre-head is that, and the post-tail is that. Charge is 0. So that looks right to me. All right, so change this, DHA, DH. So what happened here? Weird atom valence. Oh, I see what's going on. Yeah. So we need to change one of these. What is it, C3? So it's because there should be a double bond there. Which I thought I fixed, but I guess I didn't. So we can just do this. Which of these is a double bond? So it's just saying had double bond between the carbonyl groups, which is kind of wrong. Okay, let's try something. See if this works. Yeah, so we gotta fix this too. So I think I did it right here. No, it still doesn't work. Okay, so we need to fix this then. What? Why does it open up in Chimera X? So is this the same? No, it's not. Oh wait, it might be. Oh yeah, it is. Okay. So it's something with the mol2 creation. Or it could be this. No, it's the same deal. Yeah, so the valence has to do with when we're creating this mol2 file from here, the double bond isn't taken into consideration. Explain to me how this code works. Specifically, how the mol2 is created. copies everything. So one thing I am noticing about this is that the outgoing mol2 file has the wrong valence assignments, which leads to this error later on. The main issue is that we need to recognize where a double bond is and assign the bonding properly in the mol2. Can you rewrite the code to fix this and recognize this automatically? I've done this before. So in this mol2, like, it should be a double bond, like kind of how this looks, but it's a single bond, so doesn't preserve or correct the atom types and bond orders. Okay. So copy, paste, copy, paste, because it's going to overwrite that. Oops. So hopefully what it writes will be correct. Honestly, I wonder if we could just do this. And then I think there's how do you in PyMol? I wonder if this will work. Okay. There we go. So yeah, it should look like that. So file, export molecule. All right, let's see if this works. Yes. Yeah, okay. Um, so maybe we can run this back with just how it is. Pythons for this should be okay. All right, let's see. I wonder if that'll change the charge assignments. What was it before? Regardless, this looks right. So let's see if this command works now. Yep, okay. All right. So I need to make some notes here. So what I do is take an optimized structure from ATB and then specifically the .pdb file. I load this into PyMol and then adjust the bond order there like this, for instance. What? So it'd be like now, I kind of want to go back and see if the charges are any different. So we'll save this as a mol2. File, molecule, save, mol2, and we'll do like underscore test. And then so we'll change this here to underscore test. Cap atom should be the same, and we'll do test here. And then we'll run this back. Python, oh, we need a conda. Activate that. Failed to load mul2. Did I rename it wrong? So here we have a single bond. I don't get it. What? It's weird. It's right there. But that works. Am I tripping? I guess we can just do that. Okay. Is there something different with the cap atoms? There should be the name the same. O2, C5, C6, N1, H4, C1. Maybe that. I don't think we're parsing that though. No. I'm really confused now. DHA underscore ATB. What? But that works. All right, hold on. So let's load this again. File, first structure export molecule, save. Mul2. Yes. Okay, now it works. So we're getting a bunch of this crap. All right, so the charges here look like that. For the normal DHA, they are the same. So I don't think it really impacts the calculation. So it's fine in that regard. But this is the correct one. So let's change this back to here. Do we get all those print statements? No, we don't. Oh yeah, we do. Same deal. Okay. But now, the resulting thing, it looks like that. Yes. All right. Um, it is important that you do make sure the bonding is correct for downstream commands with anti-chamber. Okay, so I think we just leave it. We don't change the code, but all right. So change this back. We are going to remove DHA just for test. All right, and then we can do this again. And we should probably do ZDB again. Cool. All right, so we can move this into there. And then we can move this into there. And then these commands should work out the gate now. Yes, sweet. All right, and then, so right now, making it so Amber can read this and be happy. We're creating a .ac file, so it has all these atom types here that Amber recognizes. So the main chain file, we're lopping off the capping residues here. Okay, we're creating the FRC mod file. And then we need to write a tleap file, which we can just copy this. So this could be DHA, DHA, DHA. Tleap, myself tleap. Prepin was not found. Why did it name that? Am I missing something? What? Object file name. That's what I'm doing. What? What do you mean? What am I doing wrong here? Oh, forgot the sequence? Okay. so we can look at AA. Yep, looks good to me. Um, and let's save it as a mol2 because I want to see something. Is the bond order correct here? Instead of 1, let's do 2. No. Hmm. I want to make sure there's a double bond right there. I mean, it must work. What are some other options we can save it as? Default atom type seems to have a bug. Um, for CMod file. I think it's fine. I mean, charge is neutral, right? All right. So we got that. So let's move on to ZDB. Copy, paste, paint that. What else do we need? Copy, paste. And then we could do ZDB again. So here, let's remove don't need that anymore. Could have those two. So that's the PDB. So here's how we would do this. Go to ZDB here. So single bond. But what we want to do is Boom, boom. So we'll unbond. And then we'll do that. File, export molecule. Save it as a mol2. Do ZDB, square ATB, mol2. All right. So if we look at this, it's got that double bond. We could do this again. So DHA would do ZDB, cap atoms. I think the cap atoms will be the same. Just double check. O1, C4, C5. Yeah, that looks right. And 2, H9. Yep. Okay. Python. All right. No idea why it switches placements of this, but that's what we got. So here we can drag over the commands here, put it in that, and then drag that over. CD, C, and B. Now we should be able to run these commands out the gate. Yep. And so the MC file should be the same too. Yeah. Main chain. C3, omit name. C5, all these H's, yeah, looks good. Got that. You could do touch t leap.n, then create this. So we need to add a sequence here. Change the commands here so it matches. And that should work. Tleap, minus f tleap. Oh, I didn't save it. Boom. All right. So we have ZDB and DHA. I think that's the right way to go about it. All right, so now at this point, we can start building rings. So we're gonna we're already building a ring. So helm2 unmodified, this actually should be modified. So we're changing ZDBs here. We need to change this to a serine now. So the way to do that, so this is going to connect to there. Wait, no, there. All right. Here's a song rec. So we look to this, flip this around to there, atoms. All right. So this is, we'll start here. So O, well, let's look here. N, where's the N? N on serine 52 should be changed to N2. So change that to N2, DHA. Then we go to CA, should go to C3. Just set to DHA. So what is C? Is this C? Yeah. C should change to C2. And then O should go to O1. And then we got probably this one, CB, should go to C4. And then OG, we're going to get rid of that. All right. So that's that. And we need to change these three needs now, which we already have a way to do that up here. It's 348. Is that dehydrated? Hey, up here. Ruby. Um, I was figuring out where are all the dehydrated residues. So this is us. So DHB. So the threonine before the serine that we just changed. Right there. So this needs to be ZDB. And so the way to change that is to select by column and go to OG1 and stop there. Okay. We can comment these out. All right. And then I thought there was one. Oh yeah, so the serine right here doesn't matter. But so there's going to be the cysteine proline, and then that threonine needs to change right here. And then there should be another one right after that changes. And then finally, right here is the last one. And comment these out. All right, and the serine doesn't change, yeah. Okay. All right, so what is this? Let's change this to modified. All right, so here we're specifying, so we need to do this for each thing. Just get rid of that. We'll do check initial charge. How are we gonna do this? So we'll call this ring A. And so after this, do ring B. Just copy all of this. And I'm going to feed this into ChatGPT, make it look neater. So ring B is a little bit different because we have a serine. So instead of 46, does it have the numbers here? No. So we just have this up and to the side. Where's the other serine? There. So instead of 46, it'll be 56. And then this will bond to, forming a bond between 56 and the C, is it called C2? C4. And it is residue 52. Do we flip the carbonyl center? So let's look at go here. Yeah. Open in terminal, code. So this is B ring. I don't think it really matters, actually. What does matter is this proton. Right there. I think it'll be protonated the same way. It's just the has a different stereochemistry because the whatchamacallit, the ranking changes. So I don't think we have to flip. But we do need to retype the atoms. These can just change to 5s, I think. Yeah. And then this can be fine. So now we're adding a proton to this. So let's see if this works. Let me go here. Missing heavy atom. 42, 43, 48, 58, 59, 60. Missing heavy atom C1. A52. Interesting. Oh, I see. Um, All right, all right, all right, all right. This. So we need to figure out what this is called. Here. It does have a C2. Oh, wait, 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 wait. I think this would be called C4 now. And then the atom after that is C3. That works. That works. That works. Set atom type H4 to H1. So it would be the equivalent of H4. So think about these. So this needs to be H5 and H6. So now we're creating a new atom. And then we're going to add it um, to here, C3. Yeah, so it should be fine. So let's do these. That works. That all works. Okay. Yeah, sorry. Um, no, don't apologize, bro. Yeah, I figured it out. It was just like some stupid error, honestly. I rebuilt it and it worked fine. It's probably the first thing I should have done. Is just try to rebuild it from scratch. All right. Cysteine. So this is going to connect to that. All right, so I think we got ring B figured out. What's the total charge on this? Close to 1. All right, so we can dupe this. Now I think ring A is the only one that has the strange stereochemistry, so we don't have to flip any other things. So delete that. All right. So now ring C, which we have up here. So this will bond with that guy. So it's 61 to 59. Or is it 58? Might be 58. Yeah, it's 58. So it's this one. So we change 58. This is 61. Wait. So this is 58 right here. 58. 58. No, that's 61. Move in the hydrogen. Let's be bonding to there. But this is 61. And then this will be 61. All of these are 58. And then we're going to add this to 58. Okay, and that should be it for C. And ring D. Let me just double check. 61, 58. Yeah. And then, so this one would be 65. This would be 62. So 65. These are 62. 62. 62. 62. All right. Nice. Okay. I'm not sure why the unperturbed charge now is that. It starts off as -1. But this should be it. Do we do relax? AA. I mean, what's the point of the relax command if it doesn't fix anything? But okay. All right, let's let this into. Do we have time left? see if we can get another one going. Supercomputer has been good to us. So let's change the names here. So we'll do HAL A2 mature. Then we'll remove that. We'll change this to what we normally have, which is PARM7 and RST7. And yeah, tleap minus f tleap. There we go. Oh, nice. Thank you, supercomputer. So we can put this, where are we? That. And I could make it titratable. So I just go ahead and do that. Let's see if it runs first before we do all that stuff. Oh, did something happen here? Did it only ask for 20 minutes? Why is this taking so long? All right, and from here, copy that, paste. We'll copy this, paste. We can load this. We need to change these to that. And that should work. We have to delete the CUDA though. Uh-oh. Here we go again. It might be due to the hydrogens, honestly. That's what I'm thinking. The hydrogens are literally superimposed on top of each other. So I need to figure that out. I think it's the hydrogens. Says Claude. I reached my session limit. Can you rewrite this so that when we add the so TLEAP set element. Oh wait, hold on. I think I saw something. Set position command. Um, guess chords. Is that a command? I don't think guess chord is a thing. Yeah, it's not gonna work. Yeah, guess chord isn't a thing. Translate. So maybe we could do like um how do we get the position of something? Mm, I mean, I know atom info would be one thing, but center, bond by distance. What does that do? Unit max distance would be that. Um, this is not a command. Here are ones available. Maybe a bond by distance one will work. I think that'll work actually. Unit residue atom. So maybe you have to select it first. So let's do all this. And we'll do that. That's not gonna work. I think it's bond by distance. Unit max distance. What does unit mean in this scenario? 1? No. You just select 1 like that. Maybe I have to do this. And then do bond by distance. Argument 1 is type atom must be of type unit molecule. H12 does not have a type. Did it at least make the PDB? Yeah. There needs to be a hydrogen there. Um, So let's do this. And then does this work? Does. So do DESC. So now I have an H12. So maybe we'll do okay, that seems to work. Right, let's see what this does then. So we'll do tlead H12. Oh, I didn't save it. So I should get rid of the first one. Yeah. And then 52, and that's H9. Wait a minute, hold on. This should be back to H12. This is 62. H12. All right, let's see if that works. Okay. Let's see if we got H's in the right spot. Ooh, looks like we do. So we have a hydrogen right there. So this should be H12. Yep. Nice. And then we could always invert the stereochemistry here too. This is ZDB. So where's the other sulfur? Right here. And so this is going there, which, yeah, that has a H9. All right. All right, let's see if this fixes the error. I think we ran out of time. Come on, be nice to me. All right, I don't think it's gonna be nice to me. What we can do is just do that. Yeah. I don't think we're using the GPU anyway. First we gotta do this. perturbed charge of that. -0.7. So that's kind of concerning right there, actually. But we're going. I think we're going. So anytime you see an error like that, it's definitely how you set up the system. So that's good to know. I don't know why I would have a minus. Wait. I get why it has a -1, but not a minus 0.7. It's going really slow. Mm. Yeah, that's taking too long. Let me just submit the job. So I'm kind of unsure why this is stopping here. Um, heat watt.md out. Did this fail? No? Oh. Wait, am I an Alex? Um, everything ran through. So we got min all. Do we do MD heat yet? Min watt, min all, heat watt. Yeah. So it should submit. Okay. That was weird. All right, I think I'll pause here. Maybe I'll come back tonight. Um, but I need to figure out why this is a negative charge. I'll probably do that later. I get why it's -1, but not why it's more than that. All right, I'll see you.